Hello everyone, I'm Ehsan Toreini and I'm coming from Surrey University. I'm a lecturer in cyber security, but previously I was a lecturer in computer science in Durham University and associate researcher in Newcastle University. And today I will talk about my research on physical security. So let me first start by saying the obvious thing, that what is authentication? Authentication is usually regarded as a process to ensure an entity is what is claimed that is to be. Usually it's done by three means. So what you know, what you are, or what you have as a shared secret. Thank you. And that's what I guess. Could be biometric or could be a special asset that you have and you want to do that. In terms of physical item, that could be a protection mechanism to make sure if that item is genuine. And that could be any sort of protection against counterfeiting, forging, cloning, tampering, or any other sort of physical changes that might happen to a genuine product or a counterfeit product. So let's review what's going on in that aspect. So, for example, what are the mainstream physical authentication mechanisms that are out there? So usually what is happening is for protection of a physical item, you are adding another secure component to that item. And that somehow means you are just adding on some seals on it, you are putting on some system on chip, the things that is happening in a lot of identity documents or passwords or RFID tags. So if I want to kind of formulate what I said here, is you put the root of trust as an integrated component. And that integrated component could be bypassed, could be cloned, could be replaced, or could be tampered with. So let me give you a little bit of a concrete example. In a lot of cases for security protection, we use a combination of methods or a concept that involves various techniques that is, in general, we are going to call them security printing. What is security printing? Security printing is especially a series of methods that tries to use special materials to make that are really hard to acquire. That's the first hardship that they have to overcome. And second, they are very much accurately measured when they are being printed. There are a few examples over here that you might have came across. So it's like a very detailed printing over here, or the sort of using an ink that is when only you can see it under a special radio frequencies, or using these sort of holograms. But you have to bear in mind that we are talking about an expensive process that is only accessible or only reasonable when you are doing it in scale or in large quantities. So the security printing has a lot of new challenges, considering everything that is going on in technology. The first challenge is the darknet. So the first thing that we are talking about is there are a new generation of criminals that are happening, that are just showing up everywhere. The first thing is because of the popularity of commodity printers. They are getting really good in printing genuine looking stuff, and they are quiet, accurate, at the same time they are cheap to acquire. Also because there are normal people, for governments they are really hard to spot them. And of course, the transaction or anonymous transactions such as blockchain, such as Bitcoin or the darknet is making it more complicated because it makes them anonymous at the same time. So let's see what we can find in darknet. First, this is an old 50 euro, and this is a very simple hologram that usually you can see in a lot of physical items. You can easily buy them in large quantities. Just look at the price and use it for your own sort of purposes. You can use commodity printers and then buy these and then have your own counterfeit. Or if you're really keen, there are instructions going on. So you can just simply follow these and have your own counterfeit. Or you are really, really motivated, you can just go and buy a counterfeit product. Just it's 100 euro, but you can buy it 45 euros, so it's reasonable. At the same time, I came across a very interesting statistic. It's just if you want to start a new life in the UK. So what I want to draw your attention is at the bottom. It's just around $1,300. You can just have a restart your life by using all these counterfeit items that you can find in darknet. So you can have a birth certificate, you can have your PayPal account, bank account, passports, a high school diploma, or if you want, a master's degree, or whatever you want. I'm not talking that they might be really real, but it's just, I want you to draw your attention that it's actually not too expensive to restart your life by accessing the darknet. So that's the first challenge. The second challenge was about COVID. So when COVID started, the criminals were really, really quick to respond. So especially in two special things, they started with these two special things. Counterfeit masks, N95, or these sort of certified counterfeit masks that you could easily buy, or COVID test kits that you can just buy in darknet and or any other means and just use them. So there, after a few kind of months, because the pandemic took a long time, they were creative and they were more daring. They were creating documents for trafficking the counterfeit medicine. And then it evolved into certification, vaccine certification. Now the pandemic is over, but the knowledge that they gained through these practices are actually reflecting in the third sort of mechanism. So this is the challenge of AI. So to give you a little bit of indication, these are stats that I gathered from the annual report of Onfido, which is one of the well-known online document verification platforms. So as you can see, between 2001 and 2000, there is an increase in medium sort of attacks. And medium sort of attacks, it refers to the attacks that are hard to see and hard to kind of like notice. And that somehow indicates that the people who want to bypass those online verification systems, they are getting better and better in terms of bypassing the anomaly detection mechanisms or any sort of forgery detection systems that they put to differentiate the genuine documents, online documents, from counterfeit ones. Another trend is the use of generative AI. So before 2021, it was quite okay to see counterfeit documents. But now you can see there are actually biometric fraud. That basically means there are, if you, as one of the processes of online verification, you have to take a selfie, or you have to record a small video of yourself. And you can see there is some sort of progress happening in that corner as well. So that means they are trying to use generative AI to basically replicate a person that somehow owns that document. And that's the percentage of the counterfeit items that is detected in that platform. And if you notice, the reason that I put them here, they're all more or less national documents, and usually they are coming with secure chips. So it's like the perception is they are secure and they are hard to counter. But apparently the trends are showing otherwise. Okay, so that was some sort of an introduction that what I am doing. So my research is focused on the intersection of physical into digital world, and basically means you have a physical object, but you want to digitalize that identity of that, and then make sure that digital form of that physical object is actually genuine and authenticate that. So it relies, the underlying research question is, how can we track and trace physical objects reliably? by using digital means. And it's something that, if I want to give a good example of it to you, would be biometrics in humans. So it's, do physical objects have something like biometrics in humans, and you can use that to track them. That somehow interprets into the transition of root of trust from an integrated part to the body of the physical object itself. So my research is focused on, can we have the root of trust as an object, as a physical object, instead of integrating something on it? There are three assumptions on that. We want to find unique features in that physical objects that are first randomly generated during manufacturing process, and second, they are extremely hard to clone. So these two sort of things are exactly the one characteristics that I am looking for in a physical object to authenticate them. So the overall process is, imagine you have some sort of document, let's say. You try to find some random characteristics in them that is shaped during the manufacturing process, means without involvement of humans. You fingerprint them, and then you use that fingerprint to authenticate that physical objects for different purposes. You can use tracking, you can use for anti-counterfeiting, prevention of cloning, tamper-evident technologies, or any sort of means that you want to have from that physical characteristics that you acquired. So, as the basic question, we started with paper sheets. So paper sheets, they come in very simple shape. They are blank, but they're used in a lot of documents as the baseline. So that was the start of the research question. So if you have a paper sheet, can we fingerprint that paper sheet based on what you have, and then can you authenticate it later on? So the answer was yes. And there was a good body of literature to fingerprint physical paper sheets specifically. But all of them, they were relying on expensive equipment or unrealistic sort of means of getting that fingerprint. So we decided to, instead of using laser beams or different sorts of radio frequency waves, we use regular light and see what's the behavior of paper sheet in presence of the light. So there are two samples that you can see. You all have noticed, if you put a paper sheet in front of a light source, you see a lot of gray areas that are randomly scattered on that paper sheet. And that was exactly the whole point. So the whole point was, those gray areas that you see when you expose paper sheet to the light, are they unique to that paper sheet or not? So light has two behaviors in presence of the physical objects or paper sheet, let's say. So it can be transmitted through that, or it can be reflected. So that's basically the first question we asked. And we looked into the microscopic version of it. So that's a paper sheet from the surface, and that's actually the body of a paper. So as first of all, the first thing that you notice is it's much more kind of physical qualities that are integrated in the body of the paper sheet, rather than focusing only on the surface. And actually, our experiments shows that you can get much more data by focusing on the transmission of light through the paper, rather than looking into the reflection of light from the paper. So, and that was the basic sort of starting point for the coming basically methods. So what we did is first start by sampling our paper sheets, evaluating them, and then coming up with an authentication protocol specifically tailored for what we acquired. So I'll start with sampling. So if you remember, the point was, first we wanted to be simple, inexpensive, and quite robust and basically efficient, let's say. So what we did is we used a simple camera, but we use the micro photography ring just for the sake that it keeps the distance between the paper and the camera constant all the time for the sake of consistency. And we use the very bulky old style light source that I hope you remember. So that was the start. And it was interesting because I'll go through the results a little bit later. But then after a while, of course, that was unrealistic. Then we changed the light source to a simple LED, which we bought from Amazon for £30 each. So it was a simple homogeneous surface of LED, and then you put the paper sheet on top of it, and you take a photo. And that's the setting that we come up with. So you put a paper on it, you take a photo of the paper sheet, and then you start authenticating that paper sheet. So the rest was somehow image processing, so I will quickly go through that. So we start by recognizing the borders and then going through the finding the efficient place and do some sort of preparation, adjusting of the box itself, and then we choose a place from the original place as we call reliable area, and the fingerprint of that reliable area is used in any other sort of authentication method that we come up with. So we have that. We found basically the reliable area. Then we go through a rather complicated signal processing, which it takes only one seconds to go through it. By complicated, that means the mathematics behind it is complicated. And then at the end, what we have is a 2048 bits of basically array which represents that paper sheet. So that's basically, we have converted the physical item to an identifier, which is 2048. So to give you a little bit of context, iris recognition has the same sort of bits. So when you scan iris, you get 2048 bits of array. And that's why I compare a lot of this with iris as well later on. So we got the fingerprint. The next question was, okay, so we want to find if it's unique or not. So that was the whole point of what we wanted to do. If we got the fingerprint and it's not a fingerprint, we cannot uniquely identify it, then it doesn't have any meaning in action. So what we did is first we designed our framework or evaluation framework. We looked into the whole 2048 bits as a whole. I'll explain it later on. And then I looked into the bits or behavior of the bits in that 2048. So this is a little bit displaying with error, but it's okay. So this is some sort of overview of the how we evaluated that fingerprint. So it's kind of like proof that we have a fingerprint, and then we just focused on the rest. So the first is we looked into if I want to simplify that text, that means the percentage or the proportion of the similar bits or similarity of the difference of the fingerprints, and this is the similarity of the fingerprints. So basically, if a curve is accumulated over here, that means the fingerprints are the same or belonging to the same sort of sample, and this basically means they belong to a different sample. And that is the bit level analysis, which kind of like goes through all the bits and tries to look at them through uniformly, randomness, reliability, steadiness, uniqueness, and aliasing of the bits. If you are interested to know more, I'll definitely drop me an email. I'll send you the paper or the original paper. But what we did next is actually putting what we wanted to evaluate in action. So we chose 100 regular A4 paper sheets from the same package. So hopefully they come from the same origin, they come from the same manufacturer, and they come from the same physical environments because they were in the same box. And we sampled each of them 10 times. So basically at the end we have 1,000 pictures, which basically means we have 1,000 fingerprints, and cross comparison of those was around 500,000 comparisons. So basically the point was we have 1,000 images. Can we differentiate each image what the paper belongs to or not? So as I said, for the sake of comparison, I'm going to compare our findings to iris recognition as well. So we managed to get what we wanted. It was 100% recognition rate, and all the same papers from the stack was recognized as safe, and all the different ones was recognized as different. And that somehow was very good start for our analysis. To give you a little bit of indication, the differentiation of this curve was much better than iris recognition, which is around 14, but the notion that is called decidability in the whole biometric recognition for us was 21, which gives us a lot of room for coming up with security protocols or designing security protocols for sake of making the whole ecosystem more secure. And more interestingly, out of 2,048 bits, around 800 of them were completely random. So to give you an indication, for iris, which is a relatively reliable biometric for humans, it's around 250. So it's like four times more than, 3 times more than iris. We are kind of like, there is more kind of strength in the randomness of the bits that we got. And that's somehow the other aspects of our results that if you are interested, you can see in all of our bit analysis evaluations, the findings are almost very close to our ideal. So, but that was actually in an ideal situation. We usually don't treat paper in ideal situations. We just try to use them like papers. So what we did is, in another set of experiments, we rotated them, we crumbled them, we scribbled them, we ironed them, we burned them, we soaked them. We tried to be harsh to that paper. And that was still the recognition that we got. In a lot of cases, basically the false acceptance rate, which is the ideal in this authentication, stayed 0. And false recognition rate for rotation and crumbling were a little bit, just slightly different, but there is a good reason behind it, because we are first changing the body of the paper or changing the kind of value of the pixels in that image that we get. So we somehow expected that result, and that's somehow the more kind of mathematical definitions of the bit level analysis that we got. So let's talk about the authentication, because I said when we did all of this, the most important part for us was looking into the authentication part. So as usual for authentication, we try to for any sort of biometric authentication, we try to look into 2 scenarios. What happens if there is a server and it stores all the templates, and then we want to kind of go through all and then one-to-many or one-to-one comparisons to come up with a genuine answer of if something is authenticated or genuine or not. I will not go through this, but to give you a kind of like a snapshot, but what we get is if you imagine you have a central database in around 10 to the power of 10, we will likely get 10 to the power of 20, we will likely get a conflict. But for iris, it's around 10 to the power of 10. And that's one of the reasons that iris is still a very good biometric measure, because the probability of having a conflict in a central database is less than the population of Earth. So what we had is actually very reliable sort of conflict-resistant data set. But what I want to focus a little bit on is on the offline authentication. So what do I mean by offline authentication? I mean you have some sort of representation of the digital sort of fingerprint that you get, and you have a device that you can trust, hopefully, and then without any sort of communication with the server for transmission of the data, you will be able to authenticate that. this QR code. So the first question is, do we want to expose the fingerprint as public knowledge or not? And I kind of was against that. So this QR code shouldn't involve the fingerprint itself, for the simple reason that there are a lot of valuable items that we like to protect against protect the fingerprint. The most simple example could be the collectibles. So for example, if you have some sort of artwork, you have some sort of historic item, you don't want everyone to have access to your digital fingerprint, and that's why we prefer to lock it in the first place. So, but the key problem here is the noise, because when you get two fingerprints, they are very similar, but there are slightly different bits, and that's good for the sake of the analysis, but that's bad for cryptography, because we want to, if it changes, that means it's hard to authenticate it later. So we looked into the noises that we get. If you can see, these are the two examples, partial of that 2048 bits. You can see what we get is a combination of single or group errors. And that gave us a room to be innovative in using combinations of error correction codes. So we decided to use Hadamard in combination with Reed-Solomon, and for the sake of reason that combination can tolerate to the error rate of 27%, and what we get in similar, it was less than 25%. So we were safe in terms of using the sort of error correction code that we get. So the authentication protocol works like this. You have K, which is chosen randomly. It's 140 bits. You generate a pseudo fingerprint by using the Hadamard Reed-Solomon, 2048 bits. You have the paper, you get the fingerprint, you XOR these two together, you create a locked fingerprint, and when you do this, that means you are protecting the fingerprint itself by using a random key. And what you next do is you put the hash of the key and digital signature of both of them as the QR code. So that would be the registration stage, but for the verification stage, what you get is you read that 2008 bits, you read the fingerprint again, you XOR these two together, and at the end, what you get is a K prime, and if the hash of these two is similar to the recorded hash of here, and digital signature matches, that basically means you are fine. You don't know the exact fingerprint, but you know your version of fingerprint, which is tolerated by some sort of noise. So another question was, so we have that authentication protocol. Is it resilient against different sorts of attacks? So we have a robust sort of security analysis. I'll go briefly through some bits that are more important. For brute force, we are talking about a bit, complete brute force. We are talking about 2 to the power of 2048, which is impossible computationally. So we are safe for very naive brute force attacks. But what about the correlations and knowledge of the correlations? A little bit more intelligent attacker. So there is some sort of threshold analysis considering the number of bits the number of random bits, completely random bits that we get, and the width of the whole basically the analysis of that 27% of errors. And what we get is, even in the best possible knowledge that you can get from the fingerprint, there is still 2 to the power of 133 attempts that you require to guess all the other bits, which basically gives us a lot of room to claim it's impossible at the moment, considering the computational power that we have, to have any sort of brute force attack to it. So to give you an indication, for iris recognition is 2 to the power of 44. So if you know the correlation of iris recognition, you can actually get to the recognition or the iris quite simply. So the output of this research was published in ACM Transactions on Privacy and Security, which is one of the esteemed journals in the field. But that was not enough for us. So we wanted to look a little bit more. So we had paper sheets authenticated, hopefully with a good number. But how about polymer banknotes? Polymer banknotes was a good case because, first of all, they were translucent, and there are a lot of other security mechanisms that are implanted here. So it is first of all published in TIFS, which is another very good journal. The key question is how we can authenticate polymer banknotes in presence of using the same techniques. Polymer banknotes are specifically an interesting case because, first of all, they are flexible, they are more durable, they are advertised as they are more secure, and they are more resilient against these sort of harsh attacks, and they are basically everywhere since 2016 in the UK. We looked into the data from Australian Central Bank, and this is the number of counterfeit banknotes that it's circulated from 2005 to 2020. And you can see, although the polymer banknotes was advertised as more secure and is there from 1992, the problem of counterfeit is still there. It's not vanished. And that somehow is against what the core claims of counterfeit, the polymer banknotes. So basically, we first looked into the process of printing a polymer banknote. So if you go through the whole process, in one of the processes, which is called gravure, or intaglio printing, which gives that feeling of let's say, a little bit of texture to the body of the banknote. It goes through two presses, and that process gets a little bit of air blocked in the body of that polymer banknote. So next time you hold a banknote, just look at the translucent parts. I put the areas that we investigated. And you can see the air bubbles are quite different in all of this. And that was a good indication for us that it can be, although it is translucent, we can still work on the fingerprinting. So instead of using a camera, which we did actually, we tried to look into more scanning items as well. But that was an interesting case for us because the banknote itself, they come with protection mechanisms that is called Eurogen constellation. And what it does is if you want to scan a banknote and and the scanner sees these patterns, then it will stop the scanning. So basically that means you cannot scan a banknote because of these protections. But if you use negative film scanners, they will blend into the body, and you can scan a banknote by looking into that negative film. And that was exactly what we did. So we went through the process of scanning a large number of banknotes and then looked into the number. And I'm not going to bore you with the process. The same sort of methodologies is implemented with better numbers. So the decidability increased from 800-ish to 900. And you can get even more. The degree of freedom is 900, and decidability is better than paper fingerprint. And the takeaway was actually we can fingerprint polymer banknotes, although it's translucent, better than paper sheets, which was of a surprise for me as well. So am I right on time, or? Okay, good. So with that, I like to conclude this talk, but after the publication of the papers, we got a lot of attention from different sorts of groups, but these are a few snapshots of the paper, of the news items that was published these findings. Especially, I'm very much proud of The Economist and Wall Street Journal, and they were very rigorous in terms of their questioning me. So based on these methods that we had two patents in the US, which is focused on the authentication of physical texture and physical items in general. And as a wrap up, I can say this method is used to verify documents or legal documents in the different use cases. But the three qualities of doing it cheap, doing it quick, and doing it secure is actually what helps us stand out to other sort of mechanisms that are out there. And I see potential for other means, such as artworks or other physical items, specifically on the identity documents, which hopefully will be the next step of this research. So my research is a little bit more than that. I just wanted to point you that if you are interested to talk about web security, these are the things that we can talk about, and on trustworthy machine learning, these are the topics that might be your interest. Specifically, there is we actually from yesterday, we have which was a very interesting experience for me. This is an art exhibition about the security and privacy of IoT and medical IoT devices, which is held in Royal Holloway University, which was a EPSRC project. And with that, I think I can conclude my talk. And thanks for listening.